Now that we have some Laplace transforms under our belts, and we've figured out how to do both Laplace transforms and inverse Laplace transforms and apply them to initial value problems, let's move on to another thing that we can do with them. And specifically, we're going to talk about the products of transforms. These two both have formulas on the page, so feel free to go look those up. Now, here's our definition. If f of t and g of t are piecewise continuous functions on that interval, 0 to infinity, then the convolution of f and g is this thing. So f star g, note the notation there, the convolution of f and g is denoted like that, is the integral from 0 to t of f of t minus tau times g of tau d tau, or if tau's weird you out, sort of the one-legged pie, then just use, okay? Maybe it's worth noting here that the convolution is commutative. So f star g is equal to g star f. You can just make these a w substitution that is t minus u. And then what you'll end up getting with is dw is minus du. That thing will change to w. That thing will change to t minus w, and then these things reverse, and then you use a minus sign. So feel free to work through that. We might need it. We might not. Okay, so this looks extremely convoluted. Yeah, okay. All right, that's enough. Let's try one, and a little bit later we'll see why this is useful. Okay, let's try the convolution of e to the 2t and e to the 3t. So I want e to the 2t star e to the 3t. So integral 0 to t of f of t minus u, g of u, du. So we plug some stuff in. 0 to t. Okay, so e to the 2 t minus u, e to the 3u du. 0 to t of e to the 2t, e to the minus 2u, e to the 3u du. Keep going. Let me do two things at once here. So first of all, I can pull that e to the 2t out since it's a du integral, right? And then I'm left with e to the u in here, which is my favorite. And so I get e to the 2t times e to the u from 0 to t. Keep going, e to the 2t times e to the t minus e to the 0 is 1, and so I get e to the 3t minus e to the 2t. And there we go. So that is the convolution of e to the 2t and e to the 3t. Okay, now, why is this useful and why are we bringing this up now with Laplace transform? Well, here's why we care. The Laplace transform of the convolutions is the product of the Laplace transforms. That is pretty cool. So the Laplace transforms of f star g is just capital F times capital G. Now, it's not usually in this direction that we want to use it. It's usually in reverse, and that is the inverse Laplace transform of the product, which, remember, we're over here in algebra land. Products are very common in algebra land. If I know what each of these two Laplace transforms are, then I can find their convolution back in IVP land, and that it will be equal to the convolution of those two things. Okay, so let's try an example here. Suppose that I have the inverse Laplace transform of 1 over s minus 2, s minus 3, which is the inverse Laplace transform of 1 over s minus 2 times 1 over s minus 3. Let's try this using partial fractions. So let's see. I'll have a over s minus 2 plus b over s minus 3, which is a times s minus 3 plus b times s minus 2 all over s minus 2, s minus 3, and that's equal to 1 on the numerator. So I have a times s minus 3 b times s minus 2 equals 1. We'll do this the cheater way. Plug in s is 3. And what does that give me? That gives me b, a is gone, b equals 3 minus 2 is 1, b equals 1. And then when s is 2, I get a is negative 1, because that is negative 1 equal, negative 1a equals 1, so there we go. And so I would need to find the inverse Laplace transform of negative 1 over s minus 2 plus 1 over s minus 3. And just consulting our our Laplace transforms page, this is just negative e to the 2t plus e to the 3t. If that looks familiar, well, maybe you can see where we're going to go. All right. Let's try that using this theorem above. All right, so using the theorem above, we'll take this approach right here. And so the inverse Laplace transform of 1 over s minus 2 times 1 over s minus 3 is the convolution of 1 over s minus 2 inverse Laplace of 1 over s minus 3. So it's the convolution of these two things. All right, well, we know the inverse Laplace transform of that. It's just e to the 2t. And we know the convolution of this thing, e to the 3t. And what is the convolution of e to the 2t and e to the 3t? Well, we just did it on the previous page. It is e to the 3t minus e to the 2t. E to the 3t minus e to the 2t. And we can see that we got the same answer above. Now, if you're not feeling like this is, a good method yet, yeah, it's fine. We're trying it on something that we can do multiple ways to kind of give it a try first. All right? Let's try another example. Now, before we do that example, I want to go through a convolution here, and I'm just going to kind of talk us through this rather than writing it down, because I think maybe, or when I was making these notes, I was thinking, number one, that I didn't want to have to write all this, and it was easier to type, and number two is to be sort of, as you can just look through all this stuff, you can appreciate it might be hard to keep up. And because it's just tons of grossness. So what about cos t and sine t if I take the convolution? You can totally do this, but it does require 3 different trig formulas. So let me just walk through it here. So cos t star sine t is t minus tau sine tau d tau. And I did all of this in taus. First thing, use the angle addition formula. So that's cos t cos tau. The sign changes plus sine t sine tau, and then that thing just stays the same. Then you take that thing and distribute it to both of those terms, which gives me cos t cos tau sine tau and sine t sine tau squared. Okay, still with me? Now, I'm going to break this up into 2 different integrals, that one and that one. And then this is a d tau integral, so the cos t will come out of the first one and the sine t will come out of the second one. So I'm left with cos t and then the integral of cos tau sine tau, and then sine t, the integral of sine tau squared. The one on the left is kind of simple. This is just a basic u substitution here, with u being sine, and then du is cos u du. This one requires some power reducing, which admittedly is one of the formulas I have to look up. I can prove it, but I don't don't want to have to prove it every single time. So I haven't put it in my head. Maybe put it in your head, so you don't have to be like me and have to look it up for 10 years. So I say 10 years, 20 years. 1 minus cos 2 sine squared tau is 1 minus cos 2 tau with a 1/2. Once we get to here, we are just in the land of Calc 1, and it's no big deal to get down to here. Okay, now this is just integral of 1 is tau. Integral of cos 2 tau is 1/2 sine 2 tau. And at this stage, plugging in 0, sine of 0 is 0, sine of 0 is 0, sine of 0 is 0, and when tau is 0, it's 0. So at 0, everything goes away, and I'm left with only tau is t left. So put in t there, put in t there, I'm left with this expression. And at this stage, I'm kind of done-ish, except this simplifies a whole lot. And so you can do some distributing, this thing going in here. And then what I have is this 1/2 t sine t, and the other ones, cos t sine squared t and sine 2t sine t. I can do some double angle formula business, and so this turns into 2 sine cos. And when you do that, the two sines go together and you get a cos, and then this thing cancels this thing, and all you're left with is this middle term here. So feel free to go through that again, but here is the deal. The convolution of cos t and sine t is 1/2 t sine t. Okay, so feel free to just know that one if you like. Now, what will happen, okay, as a next thing, what will happen if we try and do partial fractions on this thing right here? Well, what I would get is, as plus b over s squared plus 1 plus cs plus d over s squared plus 1 squared. Now, do I want to go through the whole thing? I don't know that I do. So here's going to be the deal. When you go through all of this, you're going to end up with the c being 1 and a, b, and d all being 0. And what that means is that you just get this thing back again. So it doesn't actually decompose any further, okay? So we can't use the partial fractions to split this thing up into things that we might know the inverse Laplace transform of, okay? And so let's try to do the inverse Laplace transform of s over s squared plus 1 squared, but instead of doing it the partial fraction decomposition way, why don't we just try our new thing, all right? So the inverse Laplace transform of s over s squared plus 1 squared, so I can put one of the s squared plus 1's there, one of the s squared plus 1's there. And this turns into s over s squared plus 1 convolution inverse Laplace transform of 1 over s squared plus 1. And which one is which here? So the one with the s on top is the cosine. So this is cosine t convolution with sine t. All right. And I happen to know what that is if I go back here. That is 1/2 t sine t. And so here's a problem that we couldn't do before with our previous techniques. We needed some new techniques to help us with this one. Now, there might actually be another way, using derivatives and integrals, and I'm not going to argue that. But here is a way to do it that we couldn't have done it with just partial fractions. Moving on here. Here is one that there might be a homework problem on you showing where this thing comes from. So if that's the problem, then you get to do it yourself. But I'm going to just assume it right here. So the convolution of sine with itself is 1/2 sine t minus 1/2 t cos t. Now, what are we going to do when I want to do the inverse convolution of 1 over s squared plus 1 squared? Now, this is very similar to the one that we just did. Convolution of this. And this one is sine t, convolution with sine t, which I'll just copy down. 1/2 sine t minus 1/2 t cos t. Very good. Now, I want to do one more example here, and on this page I decided to type a bunch of this work because it was going to be kind of tedious and lengthy to keep up with, much like that convolution with cos t and sine t example. So here we go. Suppose I wanted to find the inverse Laplace transform of this thing. 32 over s squared, s to the 4th minus 16, and 32 over s times s to the 4th minus 16. Now, these are very similar right here. In fact, if we put an s here, right, and an s here, you could write this as one single thing as 32s plus 32 over just this denominator. Now, the way we would do this is by taking the inverse Laplace transform of this first term and adding it to the inverse Laplace transform of that term. So this first step is no big deal, the first term and the second term. The next thing we would do is use some partial fractions on this thing right here, okay? Now, when I do that, I know that s to the 4th minus 16 factors as s to the s squared plus 4, and then s squared minus 4, and s squared minus 4 factors as s plus 2, s minus 2. And I have done all the partial fractions already, and so it's negative 4 over that one, minus 1 over that one, plus 1 over that one. And so the inverse Laplace transform of this first term, 32 over s to the 4th minus 16, is just these three inverse Laplace transforms, which gives me negative 2 sine 2t minus e to the negative 2t plus e to the 2t. All right? Now, here's the part that I really want to bring up here, in that if you see something like this, I would need to do partial fractions over again to do this next one where I have another term. And on this problem, I don't really need to do that because this is equal to 1 over s times 32 over s to the 4th minus 16, which I already know the inverse Laplace transform of because I just did it. It's right here. And so what I can do is I can kind of leverage that result, and I can use the convolution here because this convolution is very nice. I have 1 over s with the convolution with this thing I just did. And so what is the inverse Laplace transform of 1 over s? Well, it's just 1. And so when I take the convolution of 1 with the previous answer, I'm essentially just integrating that answer, because when you put 1 here, this is the g of tau, there it is, and the f is just 1, so f of t minus tau is just, just 1 hanging out. And so this answer is just, hey, integrate that thing that I got before. And so I went ahead and integrated it, and you get that thing. Plug in t, you get all this. Plug in 0, you get all this. And this is sort of unfortunate because these aren't just zeros. So that is 1, that's a half, and that's a half. So there's the minus 2. Okay. So put that result together, right? Put this line and this line together with the first one up here, and what you get is the inverse Laplace transform of 32 over s to the 4th minus 16 is inverse Laplace transform of that one plus that one. there's the first line, there's the second line, combine some like terms, and you are good to go right there. Okay, so that was an example of how you can kind of leverage some previous results to give you further results. All right, now we are going to call this section good right here, and I will see you next time.